So, thank you to everybody for making it, making some time out of your day. Hopefully the weather's nicer where you are than it is here in gloomy Baltimore today. But I'm excited for this opportunity to speak with you all about rotary encoders. It's something that, as mentioned, I spent the better part of the last 9 years of, of my career focused on. And, hopefully we can teach everybody something. And really, this is hopefully an opportunity to get to know myself, Everett, and to see how we might be able to help one another moving forward. So, with that being said, I think we can go ahead and get started here. So in general, as automation becomes more common, both in business as well as our everyday lives, sensors are going to play an important role. As the number of applications and installations increases, so will the number of sensors used. And as quantities go up, the prices are going to go down, thus resulting in more installations. So this is really a simple feedback loop. We've seen it time and time and again in different industries and different products. And encoders in that regard are no different. So with kind of that growing market and excitement in mind, let's see what we're going to cover today. So I'll give a little background with respect to fundamentals and terminology, provide some historical context on rotary encoders. We'll also discuss the different technologies, and then we'll close with some design considerations and specifications. So at its most basic level, a rotary encoder is just a passive device used to determine the angle or position of an object. So sometimes we'll have people asking, well, do they drive motion? Do they move something? And no, they're passive. They're kind of along for the ride. And but they might be used as part of a feedback loop to a motor or a drive. And at a very high level, encoders typically fall into the following categories. They could be absolute or incremental. Now, an incremental encoder outputs a pulse every time the encoder travels a fixed angle. So a simple analogy is think of that of a stopwatch, as it counts the number of seconds from a given point. You could have a stopwatch and just hear every time it does a tick, and you could count those and you could know that 13 seconds have gone by. Likewise, with an incremental encoder, if depending on its definition, if you get 20 pulses, you might know that that is the equivalent of 6 degrees, for example. Now, at the other side is an absolute encoder that outputs a known position. So for example, an absolute encoder might give you an output of 30 degrees, and that would be with respect to a preset origin or a 0. So a good analogy is a simple clock, because it's going to provide you with the current time. So right now I can look at my clock and I can see it's 2:05, and I don't have to worry about what happened in the past or what might happen in the future. That's an absolute measurement. I can say it's 2:05. So it gives you a sense of the comparison of the two and why you might use one over the other. Just like sometimes you need a stopwatch and sometimes you just need to know what time it is. An absolute encoder would be either single turn or multi-turn. So for a single turn encoder, it's just going to roll over after a complete rotation and it'll start counting again from 0. With a multi-turn encoder, it's going to provide not only the current position, but also the number of turns. And this is a real advantage, especially in places like industrial automation, where you have a conveyor system or a linear actuator, or you're converting a rotary measurement into a linear position. So with that in mind, we can talk a little about the history of rotary encoders. And really the fundamentals for today's optical encoder was largely developed in the 1950s and 60s. The idea isn't really all that new. At the time, LEDs were new and they began to offer reliable, consistent light source. And you saw demand from defense and space applications where they needed higher resolution than what was available with common mechanical-based potentiometers. So Fundamentally, you can even see in the photo here, you have that little LED kind of in the on the left-hand side there. And there's a code disk below it. If you look carefully around the edge, I'm not sure if you can see my cursor, but you can see the lines in the disk. And then underneath that is going to be a receiver that's going to determine if light is passing through or it isn't. So fundamentally, it's a pretty basic concept, and it certainly works. It's been in the market for 60 plus years. With time and the decades that follow the development of the optical encoder, we added a gear train so you could have multi-turn counting. And then the real next big development was in the 2000s when magnetic, capacitive, and inductive encoders really began to become commonplace on the commercial market. And with each, it brings its own strengths and weaknesses. So starting with optical encoders, most optical encoders are pretty common in industrial and defense applications. You can find them with incremental and absolute interfaces. As mentioned before, you have a real broad market. Some are very low cost, maybe a few dollars when purchased in quantities, and others can exceed $10,000, $20,000 each, depending on specifications. While the sensing mechanism, the light passing through the code disk, is itself non-contact, they can have many intricate parts, especially in a multi-turn model. So if you look at the image here, which is a split up, you can see you have multiple PCBs. You have the movement of the bearings in the code disk, the gear train for the multi-turn, kind of sandwiched in the middle there. There's a lot of things here. There's a lot of mass. In short, there's a lot of things that could go wrong. It's a complicated device. The mounting tolerances are very tight, whether you have a low cost, low accuracy unit or a high cost, high accuracy unit, especially for kit style encoders, where the optical code disk might be mounted separately by the user than the receiver. Significant knowledge and skill can be necessary to achieve the encoder specifications. That being said, optical encoders were the go-to technology for decades. Low-cost encoders can still be found in everyday household items like AV equipment and printers. High-end encoders can offer extremely high resolution. 25 bits of resolution per turn isn't uncommon in a very high-end optical encoder. And these are used in laboratories as reference encoders, antennas for pointing applications, and multi-axis positioning tables. In these very high resolution applications, though, the common theme is the encoders are more or less stationary, as any significant movement can throw off the alignment between the code disk and the light and the receiver, as a result, significantly degrading the performance. Now, in between, we kind of find what we would call industrial encoders, which is the type of thing that we deal with at Everite, and you can find these in all sorts of applications: baggage handling, food and beverage, packaging, mining, oil and gas, alternative energy, and the list goes on and on. So as we go and introduce the different technologies, we'll start with magnetic encoders. So magnetic encoder is typically based on the Hall effect. These sensors entered the market as low-cost incrementals. One of the most common applications was ABS system that you might find in your car. Specifically here, we're going to use a derivative of position, which is velocity, to track the velocity of each wheel, and then the ABS system can react appropriately. Fast forward to the 2000s, we began to find magnetic rotary encoders in the industrial market. Unlike before, they're now absolute. Another cool feature that we see bundled with the magnetic rotary encoders is a battery-free, gearless, multi-turn based on the Wiegand effect. And I could do a whole presentation on the Wiegand effect. I won't now, but basically the Wiegand effect is a self-powered pulse generator for when the encoder isn't connected to its regular power supply. And as the encoder rotates, it'll eventually cross a threshold. And at that point, the potential energy is released, and it's great enough to power the EEPROM to do two very important things. One is note the fact that a rotation occurred. And second, it can note the direction. So it knows, should it count up or down? And what's so cool about the Huygens effect is it does all this independent of speed. So it's not like a dyno where the light would get brighter if you pedaled faster. It's completely independent. So you could have a rotation that's slow or fast, and it can count. And what this does is it eliminates the complicated gear trains that we saw in the optical encoders, and it also eliminates lithium batteries, which, as great as they are and as many advancements have occurred, they still have a limited lifetime, maybe 10 years. There's no reason a good industrial encoder can't be in an application longer than that. And also with batteries comes some risk. All you got to do is get a box in the mail from Amazon, and you'll see all the stickers on it if there's a lithium battery in it. These are design considerations, especially in aviation or medicine, that designers don't want to have to deal with. And the Huygens effect provides an alternative to that. So getting back to optical encoders, generally magnetic encoders are going to have lesser performance when compared. However, they're going to have better resistance to shock and vibration, water ingress, and there's multiple reasons for that. First, they're easier to protect because they're smaller and lighter. An object that has less mass is going to be less impacted by shock and vibration. You also have dust and dirt aren't going to impact the measurement because you don't have a visual measurement like you did in the optical encoder. And they're generally going to cost less. I like to liken the relationship between an optical encoder and a magnetic encoder to that between like a traditional rotary hard drive and an SSD. The rotary hard drive's been optimized over decades, and it works, and you still see lots of them. But at the same time, there isn't really a whole lot left to do to improve it. Whereas that solid state drive has a lot of advantages, and it's just much more rugged based on the simple fact that there's less stuff moving in it. So, with that in mind, we can go ahead and look at some, common applications. And not surprisingly, they're broad, because what application doesn't, benefit from a product that costs less and is more reliable? So we can look at things like high-speed overhead doors, water wastewater valves, solar tracking, AGVs, material handling, packaging systems, and the list really can go on here. So at the other extreme, we have capacitive encoders. And capacitive encoders came from the opposite side. They came from the defense industry and were developed originally and were rather expensive. However, they have many advantages here. They're going to be lightweight, compact, even more so than their magnetic counterparts. They have very high accuracy, robust, and highly resistant to EMI. What's cool here is if you look at this image, you can see these green and blue lines that are to represent the electric field between a transmitter and a receiver. And what this does is it creates a holistic measurement. So compared to with the optical encoder, where we are looking at one spot on a code disk, the capacitive encoder is making a measurement based on the entire surface area there. As a result, mounting intolerances, issues due to being either eccentric or tilt, there's much more tolerance for these sort of errors in a capacitive encoder. From a form factor standpoint, capacitive encoders typically take one of two forms. Here's what we would call a 3-plate, where we'd have a transmitter, a receiver, and then inside here you'll see kind of looks like a gear, and that's an interferon, and that's would be connected to the rotor. And as the rotor would turn in that interferon, it would create a unique interference pattern for that electric field between the transmitter and receiver. And that unique pattern has been mapped during manufacturing, and therefore the position can be derived from it. Now, the other option is what's called a 2-plate, where the transmitter and the receiver would be in the same plane or the same PCB, and the rotor now would act as the reflector. And again, here you'd have a unique electric field as the rotor would rotate 360 degrees. So historically, capacitive sensors were very expensive, but in recent years, the costs have really come down as volumes have increased and more manufacturers are releasing capacitive encoders. So where might you find capacitive encoders? As mentioned, obviously defense, as that's where it was developed from, in air defense and missile guidance. You also see them in vision systems and gimbals, both for visual wavelengths as well as LiDAR. Capacitive encoders are a great fit for medical robotics, where the combination of compact size, and these can be as small as 16 millimeters in diameter, 3 grams in weight or mass, excuse me, high accuracy and resistance to EMI allows for installation in locations where other encoder technologies simply can't function. You can find capacitive encoders in outer space. So for example, capacitive encoders spent 6+ years in space on NASA's Robonaut 2. Here we have lightweight, resistant to shock and vibration, are all significant advantages when selecting a sensor for space applications. And then last, as price decreases, we're seeing more and more capacitive encoders enter the collaborative robot and semiconductor assembly fields. So the ability to mount a high accuracy sensor that's resistant to EMI means that the encoder can be mounted adjacent to a motor and drive without fear of interference. Last but not least, we'll talk about inductive encoders. Inductive encoders are similar in principle to a resolver. However, the windings are condensed into a PCB, resulting in an end product that's lower cost, more compact, and easier to install. Although the two-plate form factor of some inductive encoders might look similar to a capacitive encoder, from a practical standpoint, there's many differences. Inductive encoders are ideal for large through-hole applications. We have one vendor who has off-the-shelf application or products with a 0.5 meter inner diameter. The idea of achieving that large of a form factor with any other technology and maintaining high accuracy and resolution is really quite a challenge. Inductive encoders are highly resistant to shock and vibration, but they're also resistant to things like dirt, ice, water, and other contaminants. Due to the geometry of the inductive encoder, fully redundant outputs can be easily achieved by nesting one encoder within another. This is a big advantage in critical applications where mounting only one sensor needs to be considered, and the PLC can then validate the output of 2 or even 3 sensors. And that's what we have here in this photo. You can see the inner red ring followed by a larger red ring around it. And this is going to provide 2 fully redundant outputs. Typical applications for inductive encoders include slip rings for radar systems, mobile machinery, fire trucks, excavators. Here you have these really demanding, wet, dirty, outdoors applications. Inductive encoders really excel in these places. We also see them in gimbals for vision systems. In robotics, you can find them in general automation, but also in more demanding applications like medical and subsea. For example, we have a customer who is using these inductive encoders and they submerge them in oil to withstand the deep pressures during a dive. So as important as the technology behind the encoders is, there's many other specifications you want to keep in mind, and they might help in driving the decision process. Most obvious is communication protocol. How are you going to talk to the encoder? How are you going to get that information that it's providing? So having been on the market the longest, the most options exist with optical encoders. One can find everything from incremental and analog to sine, cosine, CAN bus, Ethernet-based protocols. The list goes on and on. The other technologies each kind of seem to have their own little niche and are most commonly found with industrial standards like SSI and BIS. Another consideration is, how are you going to couple the encoder to the axis being measured? So your value of your encoder's output is only as good as the mechanical alignment. It's like buying new tires for your car, but not getting it aligned. They're only going to do so much. So for a given application, you want to think about, well, what is there to mount to? Is a traditional shafted encoder going to be the easiest with a coupling? Do you have access to the end of the shaft, or does the encoder have to go over an existing shaft in the middle? In the case of a slip ring, you might have electronics or a wire harness that needs to pass through. So there's a variety of different considerations here, and fortunately different encoder options to help. An OEM might consider a kit style encoder, where the encoder could come as multiple parts, one which mounts to the axis turning and another that's fixed. While reducing cost and size, this often adds to the installation complexity. So over the past few years, though, several encoder manufacturers have optimized these kits to make them more user-friendly. And this is typically done with easy-to-use graphical user interfaces that provide installers with real-time feedback as they put these together and how to optimize them for performance. Another consideration is, what's the environment like around the encoder? Operating temperature, shock, vibration, water, debris, EMI. These are all things to keep in mind. For oil and gas, grain, mining, and potentially flammable environments, there's entire lines of encoders with ATEX, CSA, UL, and other certifications to help maintain a safe environment. So the last thing you want to think about also is cost. What's the best encoder based on your budget? Encoders can cross many magnitudes of order in terms of cost. And that's one of the things that at Everett we really strive to do, is to understand not only somebody's needs, but their budget, and find that best option. So that being said, how can we help? Reach out, tell us about your application, what you're looking for. Not only do we have over 100 million unique encoders available to us, but each of our vendors can offer customization to meet the needs of a given application. Contacting us is easy. You can do it by phone, email, web chat, browsing the website. You can check out our YouTube page and videos there. We really do our best to be accessible. That being said, my colleague, George David, is now going to respond to some of the questions that were sent in during the web chat. But thank you so much for joining me.
Thanks, Jared. That was great. I don't see any questions. If anyone has any questions, please feel free to put those in the chat now and we'll answer those. Give me a minute here.
I guess we'll have to tell bad jokes instead.
No, I think you did great. I think you did a nice job in the overview, Jared.
Yeah,
I want to hear a bad joke.
That's okay.
That's Lenny's job.
Yeah. I thought about it. I remembered one before, but I'll send it to you.
Oh, he's here. He just unmuted.
So you want a bad joke?
No, we don't need a bad joke. I guess my only closing thought, in addition to the thank you, is I know this was a broad presentation. For some, it might seem a little basic. For others, it might seem a little too much. I hope to continue it.
Greg Vernick asked if we could address this space-related application some. And I guess things to look for in those applications are, how much radiation is there going to be? How long is it going to be there? What the materials involved are. So, Lenny's a nuclear physicist, so he's probably best to talk about those.
George, I just saw there was a question from someone about the tight tolerances.
I don't see that question.
Oh,
I
that's
see it.
That's
From
in the
Sam.
Q&A tab. Yes, Sam Kriegsman asks, what did you mean by tight mounting tolerances on optical encoders?
Okay,
You want me, George, you want to answer it or you want me to?
sure, I'll get it. But actually, go ahead, Lenny, you can get it, but you got to move your face into the picture.
I don't know how, I
Never
have my
mind.
video on, but how do I move my face in there?
There
There you go.
you go.
Is it
Okay.
on now?
Yes.
Okay, okay. The optical encoders have to be aligned very accurately because, and there's we can even send a little white paper on that describing it, because when it's measuring on one part of the disk, okay, if the disk is perfectly aligned, you know exactly where it is, and you count the pulses they go past. But if the disk is tilted somehow, then it's reading the wrong line on the disk, and and that error can be quite significant. And you don't need very much of a tilt. To give you some numbers, with the capacitive sensors, you can have your alignment off by as much as plus or minus 0.2 of a millimeter or 200 microns, which, if you know anything about alignments of optical encoders, they have to be less than 8 or 10 microns to get the highest resolution, to avoid that kind of tilt error.
Right, and
And again,
that tilt error is if you imagine a projector, and if you think about a projector projecting an image directly as it's supposed to, it looks like a picture. But if it's on an angle, it becomes elongated and irregular. And that's kind of the visualization of the effects that you get if you're mismounted on an optical encoder. And that mismounting can occur from either active, or it could be permanently mismounted, or it could happen as effect of loads in your device. You could have shifting of your device depending on how much torque or load is in the sensor, which can actively change your measurement. The higher the resolution that you need, the bigger the problem. So the more lines that you have, the more likely you are to read a false image of what you're reading.
and just when people talk about the very high resolution 25-bit for optical encoders, these are devices that are mounted in temperature controlled rooms and mounted by professionals from the manufacturer. These are not the kind of devices you take out somewhere where you're bouncing them around, because of that. But if you really want the very highest resolution and you're willing to go the extra step on alignment, that's the way to go. But without that, they really run into problems. Okay, so.
All right, we have another question here. What are the lower end on price ranges for inductive encoders?
It depends. In a packaged unit, in a packaged unit where you have it mounted in aluminum plates, in a sort of a lower resolution of 14 or 15 bits, you could probably be looking at a through-hole of about an inch. You could probably be looking at $300. On a board-based system for an application, you could probably get down into the $200 range at some quantity. But the bigger you go, the bigger the through hole, the higher the accuracy, and the higher the resolution that you need, the higher the price is going to be. We have some of them where we're selling them into a military environment where we have a dual reading, and it's the larger one is 300 millimeters on the outside and 250 millimeters on the ID, and those sensors with the requirements that they have, they're almost $2,000 a piece. But for the most part, an inductive sensor packaged similar to the one that Jared showed is going to be in the $400 range.
All right,
In
well,
low
unless there's-
quantities.
unless there's any other questions, I think we can wrap this up, guys. That was great.
Thank you very much.
Thank you.
Welcome.
Thank you. Take care.
Thanks, everyone.